It's the middle of August. The sun is dropping slowly toward the horizon over the Mediterranean, and the air above the water is starting, very gradually, to cool. The water itself barely notices. All day, satellites watching the sea from orbit have been recording the same thing. Broad stretches of water running noticeably warmer than what's normal for this point in summer. The effect is strongest in the western basin, where the Balearic Islands, the coast of Catalonia, the south of France, and the Ligurian Sea together form something like a heat core for the entire Mediterranean. Right now, as the sun goes down, this sea is holding an enormous amount of energy, built up over weeks of summer heat. Somewhere along the coast, the sand hasn't cooled yet, and fishing boats are drifting back into harbor through warm, motionless evening air. Nothing about the surface gives away what's underneath it. A huge reserve of stored energy, built up day by day, month by month, since early summer. And the real question of this film isn't how warm the water is today. It's something else. What happens to all that stored heat once the atmosphere above the Mediterranean starts cooling in the weeks ahead, while the sea itself doesn't? The summer of 2026 has been another test of endurance for the Mediterranean. According to the Copernicus Marine Service, warm conditions held on across the western basin and parts of the northeastern Atlantic for nearly the entire summer, and by mid-August, wide areas of unusually warm water were still clearly visible on satellite maps. This isn't a short-lived spike. It's a sustained condition, what oceanographers call a marine heat wave. The gap between what we see on the surface and what's actually happening underneath is what this film is really about. We'll look at why water cools so differently from air. We'll unpack the difference between surface temperature and the actual amount of energy the sea has taken on. We'll follow that stored heat toward its first real encounter with cold autumn air. And we'll try to answer, as honestly as possible, the question climatologists and forecasters across the region are asking right now. Does any of this mean autumn 2026 is guaranteed to be stormy? To understand why that question matters, it helps to look back at the first half of the year. According to Copernicus Marine Service data, the average sea surface temperature of the Mediterranean from January through June 2026 ranked among the warmest first halves of the year on record, close behind 2024 and 2025. More important than the exact figure is the extent of what happened. Marine heatwave conditions of one intensity or another affected nearly the entire basin, with large portions of the sea experiencing strong, severe, or extreme conditions for extended stretches. Nowhere was this more persistent than the western Mediterranean. Then came July. According to the Copernicus Climate Change Service, sea surface temperatures around Europe set new records in July 2026 along the Atlantic coast and across the western Mediterranean, and the associated marine heat waves were described by specialists as both extensive and severe. That's the picture. A warm western basin, energy accumulating week after week, that brings us to where we are now, in the middle of August. Before going further, it's worth being clear about what a marine heat wave actually is. It isn't just a casual way of saying the sea feels hot. It's a period during which water temperature in a given region stays significantly above what's typical for that location and that time of year for a sustained stretch of time. What matters isn't the number on the thermometer, it's the departure from normal. 28 degrees Celsius in one part of the sea might be an ordinary August reading. The same number somewhere else, or at a different time of year, could be genuinely extreme. That's why specialists compare temperature not in absolute terms, but against a long-term climatological baseline calculated for that exact place and that exact day of the year. Oceanographers also classify these events by category: moderate, strong, severe, and extreme, depending on how far conditions deviate from normal and how long that departure lasts. Through the summer of 2026, large parts of the western Mediterranean sat in the strong to severe range for weeks at a stretch. This wasn't a one-off jump of a degree or two. It was a stable, extended state. So why did the water get this warm this particular year? There's no single cause. It's likely a combination of factors, and they don't appear to have acted evenly across the basin. The western Mediterranean, the Balearic Sea, the Gulf of Lion, the Ligurian and Tyrrhenian seas turned out to be the most exposed. Persistent high pressure appears to have kept skies clear over this region for extended stretches, which would mean the water was absorbing more solar radiation than usual, without the cloud cover that normally reflects some of it away. Weak winds may have limited mixing between the surface and the cooler water underneath, allowing heat to build up nearer the top rather than being spread through a deeper layer. On top of that, sustained heat over the neighboring land likely kept the air in contact with the sea warmer as well, making it harder for the water to shed heat efficiently even overnight. The eastern basin told a different story. The Mediterranean isn't one uniform body of water. It's a patchwork of subbasins, straits, and local currents, and each part responds to weather in its own way. So it's more accurate to talk about a mosaic of conditions across the sea than a single number describing the whole thing. Look closely at a map of the anomalies, and the hotspot for this summer is fairly specific. The Balearic Sea, the waters around Majorca and Menorca, the Gulf of Lion off southern France, the Ligurian Sea between the Riviera and Corsica, and much of the Tyrrhenian Sea off western Italy. This is where the departure from normal has been the most persistent and the most sustained. The Adriatic and the eastern basin as a whole also ran warmer than usual, but less consistently. Periods of pronounced warming alternated with more moderate stretches, as wind or shifting pressure temporarily mixed the upper layer. That unevenness isn't unusual. It's just how the Mediterranean behaves. Its geography is too complex for the whole basin to heat and cool as a single unit. But if heat has been pouring into the sea all summer, why doesn't it disappear the moment things cool off a little? This is, arguably, the most important part of the story. Why water responds to the changing season so differently from air. Picture two objects sitting under a hot sun, a sheet of metal and a large tank of water. The metal heats up in minutes and cools just as fast once the sun disappears. Water behaves completely differently. Raising or lowering the temperature of a given volume of water by even 1 degree takes far more energy than doing the same to air. That property is called heat capacity, and it's what turns the Mediterranean into a massive reservoir of thermal inertia. Air over land can shift noticeably in temperature within a few hours. The sun sets, and the land starts losing its daytime heat quickly. The sea works on a completely different timescale. A huge mass of water, warmed over months, responds to falling air temperature with a substantial lag. During the day, the sea absorbs solar energy. Wind and waves mix that energy through the upper layer to some extent, but when winds are weak, as they were across the western basin this summer, a stable, very warm surface layer forms. After sunset, the sea does start releasing some of that energy back into the atmosphere, but only some, and not quickly. This is where it becomes important to separate two ideas that get conflated even in news coverage. The first is sea surface temperature, what satellites and buoys measure, the number you see on a map. The second is ocean heat content, the total amount of energy stored not just at the surface, but throughout the water column, down to tens of meters. A high surface temperature doesn't automatically mean the entire water column has warmed evenly. Sometimes only a thin top layer, a few meters deep, is genuinely hot. Other times, the warming reaches much deeper, and the system is storing far more energy that will take much longer to give back to the atmosphere. It's heat content, not the surface reading in any given moment, that determines how long this summer's warmth will keep echoing into the season ahead. There's a simple way to picture the difference. A satellite measuring surface temperature is only seeing the thinnest possible layer, something like the skin on top of a pot of milk. That skin can heat up fast on a calm, sunny day and lose its heat just as fast the moment a breeze picks up. Heat content is the temperature of the whole pot, right down to the bottom. Changing that takes real time, and unwinding it takes just as long. That's why two locations with identical surface readings can behave completely differently in the weeks that follow. Where only a thin layer has warmed, cooling happens fast, the first time winds pick up or temperatures drop. Where the warmth runs deeper, the sea keeps giving energy back to the atmosphere long after the surface itself no longer looks especially warm. Nowhere is this thermal inertia more visible than at night. During the day, both land and sea absorb solar energy, but because land has so much less capacity to store that heat, it responds much faster, heating up quickly under the sun, and, just as quickly, giving that heat back once the sun goes down. Once evening arrives, the continents, Spain, France, Italy, the Balkans, start cooling far faster than the sea's surface. And that's when the gap between warm water and cooling air widens enough to push the sea into actively releasing energy. That release happens in two main ways. The first is direct heat transfer. Warm water simply warms the air in contact with it. The second, and far more significant, is evaporation. A warm sea surface can sustain much stronger evaporation than a cold one. Water molecules that pick up enough energy leave the surface and enter the atmosphere as vapor, carrying a substantial share of the stored heat with them, what's known as latent heat. That energy doesn't vanish. It simply changes form, traveling upward with the moist air into cooler layers of the atmosphere. There, as the air rises and cools, the vapor condenses back into droplets, releasing the energy it was carrying and helping to build clouds. So a very warm sea isn't just warming the air above it, it's charging the atmosphere with additional moisture and energy, none of which disappears. It simply gets redistributed through the system. Right now, in mid-August, this system is still roughly balanced. Hot air over hot water. But that balance won't last. From late August through September, the sun climbs less high in the sky, days shorten, and the continents of Europe and North Africa start losing their summer warmth faster. This is where the central question of the film really takes shape. What happens if the atmosphere above the Mediterranean starts noticeably cooling, while the water, thanks to its own thermal inertia, stays warm for weeks longer? A temperature contrast will build up between the sea surface and the air above it, one that will likely grow as autumn approaches. And the larger that difference becomes, the more actively heat and moisture move between sea and atmosphere. It's worth pausing here to be completely clear. A warm contrast between sea and air does not, by itself, create a storm. What it creates are conditions under which a storm, if the right atmospheric setup happens to develop, can draw on extra fuel. Let's break the mechanism down. A very warm sea surface can boost evaporation and increase the moisture available to the atmosphere. It can increase the flow of heat rising from ocean to air. But turning that moisture and energy into heavy rainfall or a genuine storm normally requires other ingredients as well. It needs atmospheric instability, conditions where rising air is favored rather than suppressed. It needs a lifting mechanism, a low-pressure system, a front, or an intrusion of cold air aloft. It needs the right wind shear at different altitudes, allowing a system to organize and hold together. And terrain often plays a decisive role too, mountains that force moist air even higher. In other words, a warm sea can supply extra fuel, but it isn't the ignition switch. Fuel without an engine, without a spark, without the right setup, doesn't turn into a fire on its own. The same logic applies here. Energy and moisture are more or less always present in the system during the warm season, but whether that potential turns into an actual severe event depends on whether the right atmospheric picture comes together on a given day, in a given place. There's a related distinction worth keeping in mind, one that often gets lost in conversations about weather. There's probability, how much potential a system has in principle to produce heavy rainfall. And there's forecast, a specific claim about what will happen in a specific place on a specific day. A high sea temperature can raise the probability, widen the range of what's possible. But it doesn't become a forecast on its own without data about the atmosphere's actual future state. Data that only becomes available days, sometimes only hours, before an event. That distinction between background risk and a precise prediction is worth holding on to for the rest of this story. The terrain surrounding the Mediterranean makes this region especially sensitive to that kind of scenario. The Alps, the Apennines, the Pyrenees, the mountains of the Balkan Peninsula in Spain wrap around the sea on nearly every side. When moist air coming off the water meets a mountain slope, it's forced upward. As it climbs, it cools, the water vapor condenses, large clouds build, and, if the broader atmospheric conditions cooperate, intense, often highly localized rainfall can follow. That mechanism is characteristic of the Mediterranean and well understood by forecasters here. But how strong it turns out to be in any single case depends not on sea temperature alone, but on the full set of atmospheric conditions on that particular day. This same feature of the terrain explains something that often surprises people unfamiliar with the region's climate. Mediterranean rainfall is rarely evenly distributed. One coastal town can receive a month's worth of rain in a few hours, while a neighboring valley, separated only by a modest ridge of hills, sees fairly ordinary weather. The difference coming down to wind direction, the slope's orientation, and the precise path of the moist air. It's one of the reasons precise forecasting of these events remains genuinely difficult, even with today's weather models. It's worth briefly mentioning one more phenomenon specific to this region, the so-called medicanes, the Mediterranean's tropical-like cyclones. These are rare, generally short-lived systems that superficially resemble miniature hurricanes, but form through a different process, atmospheric dynamics. Particularly the structure of the upper atmosphere play the decisive role, and without the right structure aloft, even a very warm sea won't produce one. Claiming in advance that a medicane will necessarily form in autumn 2026 would be incorrect. Forecasts like that require knowledge of a future atmospheric state that simply doesn't exist yet. To better understand how a warm sea and the right atmospheric setup can combine to intensify weather, it helps to look at the past, not to predict a repeat, but to understand the mechanism itself. In October 2024, Spain's eastern coast, the Valencia region, experienced one of the most destructive floods in decades, killing more than 200 people. Cold air aloft met an exceptionally warm western Mediterranean, and that warmth is thought to have contributed additional moisture and energy to what became a powerful, long-lived zone of heavy rainfall. It's an example of the broader mechanism described above, a warm sea acting as one contributing factor within a much larger atmospheric setup, rather than the cause of the event on its own. Cold air aloft, a persistent area of low pressure, and the specific track of the moisture all played their part as well. It's worth stressing, the 2024 event wasn't determined by sea temperature alone. It was the result of several factors lining up at once. That's precisely why it's a useful lesson, rather than a forecast for any other year. Copernicus's own record of past years offers another lesson. In the summer of 2023, the daily average sea surface temperature across the entire Mediterranean exceeded 28.7 degrees Celsius for the first time on record, breaking a record that had stood since 2003. A year later, in mid-August 2024, that figure was surpassed again. The basin-wide daily average climbed above 28 degrees, setting a new record for the Mediterranean as a whole. These numbers matter less on their own than as part of a bigger picture. The sea isn't breaking temperature records in some single unusual year. It's doing it repeatedly, year after year. It's that repetition, more than any single record, that has kept this situation under close scientific attention. Against that backdrop, it's worth mentioning the kind of local measurement that occasionally makes headlines. In early August 2026, a coastal buoy off the western coast of Majorca reportedly logged one of the highest water temperatures on record for that specific monitoring point. It's important to understand the difference here. This is a single coastal buoy in one particular bay, not the average temperature of the entire Mediterranean. Coastal records like this are almost always higher than the average for the open sea, because shallow water near the shore heats faster and more intensely. Treating a number like that as representative of the whole basin would be a mistake. A prolonged heat wave doesn't only show up on a thermometer. It shows up in the life of the sea itself. The Mediterranean is a semi-enclosed basin. Water exchange with the Atlantic through the Strait of Gibraltar is slow, which makes its ecosystem especially sensitive to extended periods of excess heat. Scientific observations in recent years describe a consistent pattern. Heat stress drives mass die-offs among bottom-dwelling invertebrates, particularly gorgonians and other colonial organisms on rocky seabeds. Posidonia oceanica seagrass meadows, a species found only in the Mediterranean, serving both as habitat for countless species and as a natural carbon sink, are also affected. The ranges of fish species are shifting. Warm water species are increasingly showing up where they didn't used to occur, and the ranges of already established invasive species are expanding along with them. For fisheries, that means changing catch areas and a changing mix of species being caught. It's also worth understanding that this kind of stress builds up cumulatively rather than all at once. When a heat wave recurs year after year, the ecosystem doesn't get time to recover between episodes. This isn't a story about isolated catastrophic events, so much as the gradual erosion of the whole system's resilience. The Mediterranean doesn't exist in isolation from the rest of the ocean. and it's worth briefly widening the lens here. 2026 has been a record-setting year well beyond this one basin. In July, according to the Climate Change Service's monthly bulletin, the average sea surface temperature of the non-polar global ocean, the waters between 60 degrees south and 60 degrees north, came in at around 20.96 degrees Celsius, the highest value ever recorded for that month. That followed a new daily record for the time of year at the end of June, partly linked to a developing El Niño in the equatorial Pacific, which the World Meteorological Organization had placed at roughly an 80% probability in early June. This global figure can't be compared directly with a single region like the Mediterranean, but the context matters. A warm Mediterranean this summer is part of a much larger picture, one in which a substantial share of the world's ocean is experiencing marine heat wave conditions at the same time. Copernicus specialists estimate that marine heat waves affected large parts of the global ocean at various points this year, beyond the Mediterranean. Notable warm patches developed in the central North Atlantic and the equatorial Pacific, where record values for those regions were also recorded. Copernicus Marine Service's lead oceanographer described the state of the global ocean in the first half of the year as one of sustained thermal stress, a phrase that captures the situation precisely. This isn't a single flare-up in one sea, but a prolonged, widespread condition affecting several key regions of the planet at once. Now let's come back to where we started, to mid-August, to a sea holding the energy of an entire summer, and to a question that only grows more relevant as autumn approaches. What might happen once the atmosphere over the Mediterranean begins to shift noticeably in the coming weeks? This calls for maximum scientific caution, and it's worth saying plainly, nobody can say right now, in the middle of August, exactly what autumn's weather will look like in any specific country in the region. That doesn't mean science has nothing to say. It means that forecasting a specific storm in a specific place depends on future atmospheric circulation that only takes shape days, not months, in advance. But the underlying logic of the risk can be described. If the sea stays unusually warm through September and October, and the thermal inertia discussed earlier makes that fairly likely, then when significantly colder air moves in, whether from the north or from higher in the atmosphere, the temperature gap between sea and air will be larger than usual. If, at the same time, an appropriate area of low pressure develops, along with a mechanism to lift moist air over mountains, along a frontal boundary, or within a cyclonic system, then the sea's elevated temperature could supply extra heat and moisture capable of strengthening a weather system that's already forming. That's exactly how the mechanism worked in the October 2024 example discussed earlier. But it's worth stressing again, because this is the central scientific idea of the entire film. A warm sea is not a ready-made storm forecast. It's an elevated risk background condition. It widens the range of what the atmosphere can do, increases the energy and moisture available, but it doesn't determine whether that potential gets realized in any specific place, on any specific day. The atmosphere remains the deciding factor in whether the energy stored in the sea turns into heavy rain, an ordinary autumn low, or simply dissipates without any noticeable consequence. That's exactly why observations of Mediterranean sea temperature in late August and into early autumn are of such interest to specialists. This isn't about trying to predict a specific disaster. It's about understanding how much energy the region is carrying into the season when atmospheric activity typically becomes most intense. Mediterranean autumns have historically included both devastating downpours and perfectly ordinary, quiet months. Both outcomes have happened before, and both remain possible now. The difference between a warm year and a year remembered for one specific destructive event usually comes down not to sea temperature on its own, but to the atmospheric setup that happens to develop over that warm water on any given day. The sun is setting earlier now. Days across the Mediterranean are gradually shortening, and in the coming weeks, the surrounding continents will start losing their summer heat far faster than the sea beneath them. A vast body of water, warmed over months, will keep giving that energy back to the atmosphere slowly, night after night, week after week, long after the hottest days of August have passed. And that's why what we're seeing on satellite maps right now isn't a forecast of some specific storm on the coast of Spain, Italy, or Greece. It's a picture of the current state of one of the region's most important reservoirs of heat and moisture. What actually happens this autumn will depend on how this warm sea, still holding on to the energy of summer, meets an atmospheric circulation that hasn't finished taking shape yet.